So the programming model starts off with where does everything live, all the data and instructions in main memory. So main memory, as I say, is this big array. We're going to allow ourselves memory that can hold 2 to the 32 bytes of information. A byte is an 8-bit value. That's the name for an 8-bit value. We're actually going to organize the memory as words. So we're going to have a memory that's actually 2 to the 30th words. And each word has 4 bytes of information in it. And although most modern computers have a way of actually reading and writing a single byte from memory, our machine is going to be pretty dumb. It is just going to read and write 32-bit words. It's not going to have any byte-level operations, which might be a deficiency, might not. You can certainly write sequences of 32-bit operations that let you pick up a whole word and shift it and mask it to get just the byte you want. And that might turn out to be a good thing. We'll see. We'll see how it evolves here. So we have this sort of memory organized as 32-bit words, and conceptually when we send an address to the memory, we're going to be asking for a whole 32-bit value to come back. And the address that we always send always has the bottom is a 32-bit address. So it's going to be a 32-bit address, which is the 30-bit word index, and the bottom 2 bits will always be 0. And you can say, why are we doing this, Chris? This seems very complicated. Couldn't we just do a word address memory? Well, this is all sort of lost in the mist of history. We're trying hard to be compatible with machines that you're likely to see, which almost all support some level of byte addressing. So we've adopted byte addressing as our convention, but we're going to only use it to address words. So the bottom 2 bits of the address will always be 0. Okay, in terms of what's inside our CPU, our combination of data path and control logic, we're going to have those 32 registers, 32-bit registers. Now each one of the 32 registers holds a 32-bit value. So you can see this 32-bit data path, which is what you guys have built, is sort of going to be the 32-bit word is our basic building block. One of the registers will always read as 0. Register 31 will always read as 0. So that means that if you specify register 31 as one of the possible operands, what gets supplied to the ALU unit is a 0 value. If you specify it as a destination, that's like throwing the value away because you can't change the contents of R31. So if you're computing something and you really just want to look at one of the condition codes or something like that, out of the ALU, but you don't actually want the result of the arithmetic computation, you can specify a destination of R31, which causes the value to be, it doesn't change anything, the user visible state, the program state. So an attempt to write into R31 has no visible effect on the state of the machine. And then finally we have the program counter, which is the thing that's going to be incrementing and showing us where the next instruction comes from. So the fetch and execute loop is we're going to go off and fetch that 32-bit encoded instruction, and I'll show you what the encoding looks like in just a second. We're going to increment the program counter, and remember, because we're stuck in this byte addressing hell, we're going to be, when I say increment, we're going to go to the next word of memory, which means we're going to increment the byte address by 4. That moves us 4 bytes farther along in memory, or one whole word. We execute we look at the encoding of the instruction that we fetch. It's actually a 32-bit value that's come back from memory. We look at those bits, and that will tell us what to do, and I'll show you how in just a second. And then we just repeat. And if you do the design project, you'll probably be able to design a piece of hardware that can run, do one of those operations every 5 or 6 nanoseconds, which will be pretty good. Yes?
So the processor has 32 registers?
Yes.
Each of which can hold 1 word?
Yes.
Each word has 4 bytes?
Well, so I'm with you up to there, and what you said is exactly true. But for most of our purposes, you just forget about bytes. We'll not spend a lot of time talking about bytes. Each word is 32 bits. The values are treated like 32-bit values. You manipulate them as 32 bits at a time, and we go from there. Okay, so here are our 2 instruction formats. And you can see that we have 2 possibilities. We have something where we we can specify an opcode, a 6-bit opcode. So what we're going to allow ourselves is 6 bits here. How many different combinations of 6 bits are there? So our machine can have 64, which is equal to 2 to the 6 operations. Okay. The operands we're going to set aside, we're going to use 5-bit fields. How many different things can I specify in a 5-bit field? 32 things. So that can allow us to name each of the 32 registers. So in this particular format, the reason that we put little r's here is to remind us that we're actually putting in register addresses. Those are 5-bit numbers, 5-bit 01000 or something like that. 5-bit values that actually are the index of the register that we want to access. So we can in this particular format of instruction, we can specify the operands as each coming from 2 registers, okay, and the result will be stuck back into a RC register. Is that a question in the back or just a nice stretch? No, it's fine. Stretches are good. Okay, and then the second format, the second operand, instead of coming from a register, is actually a 16-bit constant. So it's very simple, right? We can do one of 64 operations. The destination of each operation is always a register. What happens if we don't want to store something? We specify a destination of 31, the binary value for 31, which is R31, which never changes even if we try to write in it. If we want one of our operands to be 0, we can specify R31, and that will always supply a 0 value as the appropriate operand. Everybody sort of see how that works? It's very simple encoding. And that's why this is a reduced instruction set computer. There's no complication to this at all. We'll be able to, when we build the hardware, we're going to use most of the bits of the instruction directly as signals in our electronics to actually control the address of the little register memory, and which value we're going to be reading out, the destination address, and then we'll just have a little ROM that will help us decode the opcode bits into the appropriate control signals for all the different things that, ALUFN and all the other things we'll want in our data path. Okay, so those are the basic instruction formats. And now I'm going to spend a few minutes and I'm going to go through and I'm going to cover, 90% of the instruction set of the machine in 2 slides, right? And the thing is that, and this should be completely understandable because these are the instructions that basically let us use the arithmetic and logic unit, the ALU.